Hello and welcome to another video tutorial. In this simple example that I am going to do is the one shown in this image. A push button or a switch connected to terminal 10, which is bit 3, of port A, will activate a LED diode connected to terminal 26, which is bit 15 of port B. The microcontroller will act as a bridge, and the objective of this exercise is only to familiarize yourself with the tools that will be used. It can be seen that an oscillating crystal will not be used, that is, I will use the internal 8 MHz oscillator. The ICPS programming channel, which I will use to program the device, will be number 2. I will also only use capacitors to eliminate noise at the power terminals. The filters recommended by the manufacturer are recommended when building a PCB for a commercial product, and the reset terminal uses the configuration and resistor and capacitor values recommended by microchip technology. On a prototyping board for electronics, also called a protoboard, I have placed what is necessary for this example. In this part we have a module that is a USB to UART converter, but its main function in this example is to obtain 5 volts for the circuit from my PC. In this part we have an LDO regulator, which converts the 5 volts of direct current to 3.3 volts. Here is the microcontroller, the power on reset system, its filter capacitors, the 10 microfarad capacitor, the ICPS bus to program and debug the code on the device, the LED diode that will turn on, and the push button. Here I have the tool called MPLAB X. It is not my intention to teach this software or the XC32 compiler from scratch. I recommend looking for video tutorials on other channels regarding these topics. Next we go to File and click on New Project. We choose Standalone Project, that is, a project that does not depend on other tools, and click Next. Then, I must choose the type of microcontroller PIC32, for which in device we can search or write the name of the microcontroller we want to use. Next we choose the type of compiler for this project, which is XC32. The next step is to select the place where the project will be received. It is good practice that each project is inside a subfolder. For this case, both the folder and the name will be the same. You can see that an empty project has been created with all the logical folders that are necessary. Note that when creating the project, it is marked as main since its name is in bold. If I right-click on the project, we can select the option to unset as main project, and its name will not be in bold. It is very important that the project is main since it is the one we are going to work with. This is even more important when we have several projects at the same time, so again I leave it as main. Since it is an empty project, we need to add the file that will contain the main function of every project in C language. I click on the logical folder source files and choose New, then I choose the option to add a new file of type C. To the new file we put the name main, and finally MPLAB X has created a file with some templates as an example. I prefer to delete them and write here the main function that is of type int. We save the file and we can perform the first compilation, which should not generate errors. And in this way, the whole project is verified to be in order. The first thing I am going to do is calibrate the configuration bits, also called fuses. I click on the top bar on the Windows option, and select the Target Memory Views option, and select Configuration. A new option opens and Configuration bit. A window opens at the bottom where the microcontroller configuration words are shown with their respective bit. The first word, called DevCFG3, is the user ID option that allows you to save a unique number that can be useful for hardware identification. The other bits that are related to the remapping of the terminals and calibration of peripherals are not important in this project since only the microcontroller ports will be used. The second configuration word of DevCFG2 is important to analyze, and it is related to the oscillator, and my objective is to work with the internal 8 MHz oscillator. Before the signal passes to the PLL frequency multiplier, it must be within a range of 4 to 5 MHz. Therefore the signal from the internal 8 MHz oscillator must be divided and the best value will be 2, to obtain 4 MHz. This division depends on the FPLL div, so I proceed to calibrate these bits, at a value equal to 2. Once a frequency of 4 MHz is achieved, it must go through the frequency multiplier, PLL. As shown in this image, the constants by which the frequency of 4 MHz can be multiplied range from 15 to 24 in steps of 1. In this way we obtain frequencies from 60 MHz to 96 MHz. This new frequency must be divided by the PLL-ODIV block, but as shown in this image, the possible values to get 50 MHz are not integer values, and the range of division values goes from 1 to 256, in steps of 2 raised to n. That is, 1, 2, 4, 8, etc. Therefore, with 4 MHz, 50 MHz is not reached. It can be a close value, that is, multiply it by 24 to get 96 MHz, and divide by 2 to get 48 MHz. So I proceed to calibrate the multiplier by 24 and the divisor by 2 to get 48 MHz. If we want to achieve 50 MHz, it is necessary to use an external 10 MHz crystal or oscillator. With the first divider we will get 5 MHz, and multiplying by 20 and dividing by 2 would achieve this objective. The next step is to configure the bits of the DEV CFG1 register. The first bits are FNOSC. If you check the datasheets, these bits refer to the type of oscillator that the microcontroller will use, as you can see in this image. There are several options for the internal oscillator. The 8 MHz one is called fast, and there are 4 options, but the option that suits us is this one, since it corresponds when it is amplified with the PLL module. So for the FNOSC option, I select FRC PLL. The FSOSC yen bit enables the secondary external oscillator, but since it is not going to be used, I disable it. The ISO bit allows the CPU to start with the internal oscillator and then switch to the external ones, but for this example it is not used, and I also disable it. The PLSC mod bits allow you to choose a variety of external oscillators, or in this example, it is none or disabled. The OSC IO-FNC bit allows you to enable the physical output as an oscillator output. We also keep it disabled. The following bits, FPB-DIV, allow us to obtain the clock frequency for the peripherals, which is a multiple of the system or main frequency, and although peripherals are not going to be used in this example, I will configure it to be equal to 48 MHz, that is, divide it by 1. The FCKSM bits enable the module that monitors the system clock. If there is an error, it can switch to any of the secondary clocks. For this example it will not be used, and monitoring and switching will be disabled. The WDTPS bits allow you to configure the watchdog post scaling, which I set for approximately 2 seconds. I'm not going to use window mode for the watchdog, so the WinDis bits remain off, FWDT on, enable the watchdog and I activate it. The bits that control the window size are irrelevant since that mode will not be used. One piece of advice is that in any embedded system, it is always advisable to use the watchdog, since no code is 100% reliable, especially when it is more complex. There is also the possibility, even if it is very small, that any electrical interference could alter the CPU's program counter, and it would skip an empty region or perform an erroneous operation. The last configuration word has the following bits: JTAG enable, which enables the use of a JTAG programmer and debugger, which I don't use, and therefore I set that bit to off. The ICSL bits that select the ICE programming channel or bus, and they will be number 2. The write protection of the program memory and bootloader memory is not important yet, so I leave those bits off. It is a good idea to always enable the read protection of a programmer, so that we do not forget to try to protect the intellectual property of our project. Now that I have finished configuring the fuses, I press the button that allows me to generate the configuration code, and another window appears with the source of said configuration. I select all the code, copy it and paste it into the main file and save said file. There is another configuration register, called CFGCon, which is not in the configuration or fuse bit. This register is in RAM, and therefore it is necessary to configure it by programming. This will be the first part of the firmware code that I will write, and it will consist of disabling the JTAG lines. Although this module is disabled with the fuse bits, in order to use the terminals or pins where this module is, it is also necessary to disable it with this register. For this, bit 3 called JTAG-EN must be at logical 0. The way to access one or more of a register is as shown in this image, that is, the name of the register next to the word bits, a period, and the name of the bit or bit. So it would be like this. I write cfg-con bits.jtag-en equal to 1. We write this inside the main function. The next step is to configure the terminals to be used as digital, regardless of whether they are inputs or output. In the microcontroller datasheets, it is indicated that the terminals by default are configured as inputs and of analog type. The registers that control this configuration, for each port, are called ANSL. For port A, it would be ANSL A, for port B, it would be ANSL B, etc. To configure a terminal as digital, the bit of the aforementioned register must be at logical 0. The bit 3 of port A doesn't have a bit associated with the ANSL register, so it is already digital by default. On the other hand, bit 15 of port B is associated with bit 15 of the ANSL register B, so it must be configured as digital. So, I write this configuration in the main function. The tris register configures the terminals of a port as input or output. If a bit is set in its tris register, the associated terminal of the port will be an input, otherwise it will be an output. Bit 3 of port A is assigned to the switch, and it is not necessary to configure it as an input, since by default, all bits of all tris registers are configured to be input. But I do it so that it looks like it should be done. While bit 15 of port B is required to be an output, so bit 15 of the ANSL register B, I set it to 0. Each terminal has an internal pull-up and pull-down resistor, which can be enabled with the CNPU and CNPD registers respectively. For the input that will be used with the push button, the pull-up resistor could be used instead of the external 10 kΩ resistor, but for this example I will not do so. Likewise, for the output it is necessary to disable both internal resistors, as indicated in the datasheet. And disabling is done by writing logical 0 to the bits of each register, which correspond to each port. Then we write an infinite loop, in which all the processes or tasks that we want the microcontroller's CPU to perform will be executed. This loop is called a super loop or main loop. The main function must return a value, according to the C language standard, even if it never reaches said return facility. In the main loop we must reset the watchdog, since remember, it is activated by the configuration bits or fuses. By writing 1 to the bit called WDT-CLR, in the Whatcon register, the watchdog timer is reset. So we write this instruction or code in the infinite white loop, which is in the main function. Now I'm ready to write the code for the project. I could just read the state of bit 3 of port A, and pass it directly to bit 15 of port B. Remember that to read the state of a bit of a port configured as input, you use the port register, and to write a state to a bit configured as output, you use LAT register. But to make the code more didactic, I'll use a conditional to determine the state of bit 3 of port A, and based on that I'll change the state of bit 15 of port B. At this point, I compile the project to verify that there are no errors in the code that has been written. As a recommendation, every time we add or modify small portions of the code of a project, we should compile it to discover errors and correct them. Before downloading the project code to the hardware, and just for this occasion, I will use the simulator. I prefer to debug with the microcontroller instead of simulating. In the top bar, we click on Debug the main project. A window appears asking us for the type of debugging tool, and I choose the simulator. The project is compiled for debugging, and then the project is running. I am going to put a breakpoint, for which I must pause the simulation. I put it in the if instruction, and with F5, I resume the simulation and the breakpoint is reached, and by pressing F8 the instruction is executed, which puts a logical 1 on pin 15 of port B. In the Variables tab, you can add the lat-B register to see or know the list of its bits. Again, we resume the simulation by pressing the F7 or F8 key. And in this way we could observe how the registers change during the simulation. To simulate the switch on bit 3 of port A, I go to the top bar and select Windows, then choose Simulator, and select the option called Stimuli. In the New tab we look for terminal 3 of port A. On the right we choose the action we want to happen. In this case I want this terminal to become a logical one, and I click on the blue arrow on the left. I press F7 until I reach the if instruction again, and we can see that this condition is true and bit 15 of port B goes to 0. The next step will be the execution of the code on the hardware. Here we have the protoboard that was mentioned at the beginning of the video. I connect the USB cable to the USB module, whose purpose is only to get power from my computer. And you can see that the microcontroller executes another code, which consists of turning the LED on and off. In the project settings, I change the debugging tool, which was the simulator, for an ICD3 programmer debugger, and in the top bar of MPLAB, I press the button that allows you to download the firmware to the microcontroller. The project is compiled again, since the debugging code was previously generated. When the programmer detects the microcontroller, the previous code stops executing, since the reset terminal is kept at 0, and then the flash memory is reprogrammed. Ready. Now I press the button and you can see that the LED is activated. That is, the microcontroller acts as a bridge between the button and the LED diode. Thank you very much for watching the video.